Good morning. Today is a special seminar. This will be a Severo Ochoa colloquial and will be presented by Professor Luis Felipe Rodríguez from Instituto de Astrofísica, de Radioastronomía y Astrofísica in Morelia campus in Mexico. And Luis Felipe will be introduced properly by Isabel.
Good morning, everybody. Thanks for coming. It's a pleasure and an honor, you will see why in a minute, to have here Professor Luis Felipe Rodríguez. He has a really overwhelming curriculum that I have to read because it's impossible to remember because of the number of merits he has and still deserves. So I will just start in saying that Professor Luis Felipe Rodríguez was born in Mérida, which is, you may know why I'm happy about. He has a PhD in astronomy from Harvard University in 1978 and a PhD honoris causa by the UNAM in 2010, where he has been full professor since 1979, so just 1 year later his PhD. He was the initiator of Mexico of the field of radio astronomy, being director of the Institute of Astronomy in the UNAM in Mexico City during almost 10 years. He created and was the first director of what is now the Institute of Radio Astronomy and Astrophysics of UNAM in the city of Morelia in Mexico, that counts with 30 researchers and is considered the institution that has the highest international impact of all Mexican science. He has been president of the Radio Astronomy Division in International Astronomical Union and has been part of a great number of committees, as well as editorial bodies of various national and international journals. Just for you to know, I mean, it's public and it's in our webpage, and those who were already here remember that he's one of the members of our external scientific advisory committee in the IRyA. His research focuses mainly on the birth and youth of the stars, and his main contributions include several, you will see, of the most important results concerning this field. The discovery of bipolar flows in young stars, the elucidation of the mechanism that excites the orbit's Herbig-Haro, and the contribution of evidence of protoplanetary disks in young stars. He has also contributed to the study of very energetic sources in our galaxy, establishing the concept of microquasars and discovering the first galactic superluminous source. In fact, what some people say, the relativity of the impatient, so that we can have access to what we don't have to in the microquasars. His works have twice earned the cover of the journal Nature. Nothing more than that. He has received several distinctions, both national and international, among which we can mention the Robert Trumpler Prize of the Astronomical Society of the Pacific for the best doctoral thesis in North America. For you who are making PhDs since now, is a good example to consider. The National Science Award, which is the maximum award granted in Mexico, and the Bruno Rossi Award for the American Astronomical Society, considered worldwide as the highest recognition in high-energy astrophysics. In 2000, he joined the National College of Mexico, which is more similar to the Collège de France. So the equivalent in Spanish would be the Academia Nacional de Ciencias, Artes y Humanidades, because in Mexico everything is collected in the same institution. In 2008, he was elected as Foreign Associate of the U.S. National Academy of Sciences, as foreign member, and in 2016, the foreign member of the Royal Academy of Science of Spain. Professor Rodríguez played a key role in the transformation of the Very Large Array into the Jansky VLA, with Mexico providing most of the resources for the suite of 7mm receivers. He has published more than 400 scientific articles that have received some 20,000 citations in specialized literature. He played a major role in the formation of young Latin American and Spanish radio astronomers. We have examples here, having directed 28 theses at different levels, but not only the number of theses, but also that his students form important research groups now both in Mexico and Spain. He also played a major role in the popularization of astronomy, not only writing a book called Un Universo en Expansión, but having written it, because this book has been provided by now more than 100,000 copies. Since June 2010, he's the general coordinator of the Mesoamerican Center of Theoretical Physics, which is an UNESCO center located in the state of Chiapas, Mexico, one of the least scientifically developed regions of his country. So I think it's worthless to say anything more. Thank you very much, Luis Felipe, for being here.
Thank you. Well, thank you for the presentation, and I'm, of course, very pleased to be in Granada again, seeing old friends and colleagues that we don't see each other with sufficient frequency. Well, this is a picture of our center in now institute, because in the scheme of the National University, centers are below institutes, so we are now an institute. And this is the Institute of Radio Astronomy and Astrophysics, located in Morelia, and I hope that you find the time sometime in the future to visit us. Today I will be talking of well, one of the most famous regions in the sky, if not the most famous, which is Orion. And Orion being the closest region of massive star formation, it is studied exhaustively. And you know, after every few years, it's good to go back and see how things are and try to do a new experiment, a new measurement. And my talk will contain 3 results. The first 2 are very straightforward and will take just a few minutes to present. And the last one is, I think, the most interesting and the one that has more astrophysics. The first one is just the measurement of distance to Orion. We will see that now with new astrometric techniques, we're getting distances that are accurate to a fraction of a % in some cases. And I'll tell you how this is done, of course, and what's the result for Orion. Then I will talk about the dynamics of the stars in the cluster that emit in the radio and that we can detect with a very large array, and we can make motions of their proper motions over the years. I will be talking of Orion, of course, of the so-called ONC, or Orion Nebula Cluster, which is a cluster of some few thousand stars centered on the famous trapezium. I will show you pictures in a second. Finally, I think the most interesting result is our studies, and many people have studied this region, a region that is called the Orion BNKL region, and which is a region younger than the trapezium, where stars are still forming, and where a remarkable explosion, not only of gas, but apparently also of stars, has been known for decades, and people have been trying to understand how this happened and what does it mean. So, you know, astrometry is, of course, the precise measurement of positions and proper motions in the sky. And when I started doing astronomy, astrometry was not seen well by people. And the reason was, I think, that astrometry had reached like a plateau. There wasn't big improvements in resolution, and new results were not coming. Well, I will try to convince you that that has changed tremendously in the last few decades, and now astrometry is an interesting field with many, many important results. And this, of course, was done thanks to the tremendous improvement in observational capabilities. And at our institute, we have a group of radio astronomers that do astrometry. And actually, there is a group, international group that this is led by a young person that is called Laurent Loinard in here. And these are the young members of the group. And then we have collaborators across the world. Maybe in here you will know Lee Harman or Neil Evans that work in the field of star formation. So this group has done a lot of results on astrometry, and I will tell you about those in Orion. Well, this is very basic, but of course if you have a source that has a velocity, you can decompose the velocity in two components, one that is radial along the line of sight, and one that is perpendicular to the radial that is in the plane of the sky. And you use different techniques to measure this and this. The radial velocity can be measured in a single night, right? Like, let's say, Hubble did the work on the expansion of the universe, and you will get the velocity of a galaxy immediately, let's say. In contrast, the study of the proper motions in the plane of the sky require of a time difference between the measurements. You have to wait for things to move. One interesting result on proper motions goes back to Galileo in 1610 when he discovered the moons of Jupiter, and here are his famous drawings with this circle indicating Jupiter and these little asterisks showing the moons around it. And of course it was the motion of these moons around Jupiter, the ones that led Galileo to interpret them as moons around Jupiter. Well, now one of the most important uses of astrometry is the determination of the famous parallax, right? If you have a nearby star and you observe it 6 months apart, this is the orbit of the Earth, you will see the apparent position of the star in the sky change in time, and actually it will describe an ellipse in the sky. It's interesting to note that the oppositors of Galileo and the heliocentric model pointed correctly. One of the arguments that the heliocentric model was wrong was that they say, well, we're not seeing proper motions in the stars. If the Earth is going around the sun, we should see proper motion. They were right, except that, of course, the proper motions are there, but they are extremely small, and it took many more centuries to finally detect the first proper motion. This was made by the German astronomer Bessel in this postage. He's remembered, but more for his functions, the famous Bessel functions, than by the detection of the first parallax. Now, we can measure the radial velocity instantly, but in contrast, the measurement of proper motion requires of at least 2 measurements separated in time. And but of course, proper motions are extremely important. If you want to have a 3-dimensional description of the velocity, you need the proper motions. It's not enough to know the radial motions. Sometimes an object has no line emission, and the only information you can get on its velocity is by measuring its motions in the plane of the sky. In some situations, like when an object is moving in a secular way across the sky, the effect is cumulative with the time. And I have found that one of the advantages of all age, one of the few advantages of all age for astronomers, is that you can get better proper motions. Because as time goes by, first the separation between objects increases. Let's say that 2 objects are receding, and then you get more data. And when you do the numbers, it turns out to be that the noise decreases as time to the -3/2. And that's very good. So with time, you get better and better measurements. Now the problem is that the effect is very small. We said that the parallaxes were of the order of 1 arcsecond or much less. The parallax being the semi-major axis of these apparent ellipses that the object describes in the sky that are actually a reflex of the motion of the Earth. And for example, an object moving at 1,000 kilometers in the plane of the sky that is located at the galactic center at 8.5 kiloparsecs will take 40 years to displace 1 arcsecond. But you can measure these things, and now you can really measure amazingly small proper motions. So let's say that astrometry had a fall in the second half of the last century, and then a rise in the last decades of the 20th century and across the 21st century. Now, how do we measure these things? Well, people measure it using different wavelengths in the optical, in the infrared, but we use radio observations, and one instrument that we use a lot that is also very popular in here, and there are many users in the public, is a very large array, which is located in New Mexico in the USA. And of course, the diffraction formula, the angular resolution is in radians, is the wavelength over the baseline. And this instrument can have baselines as separated as 30-some kilometers, and you get fairly good angular resolution. Now, of course, I cannot explain interferometry in a very short time, but just to give you an idea, in case you have never made interferometry, that if you have two detectors, A and B, and you have a source in the axis of symmetry, the waves are going to arrive at both detectors at the same time, but if the source is another place in the sky, the wave is going to reach one of the receivers first and then the other. So in a way, measuring this difference of times allows you not only to locate the position of the source, but actually to say its source and get fantastic images. This is the technique of interferometry. If you want more angular resolution than the one that provides the VLA, which is about in the order of 1/10 of an arcsecond, then you have to use other instruments. In the radio, what we use in Mexico, giving our close collaboration with the National Radio Observatory of the USA, is the famous very long baseline array, which is a set of 10 antennas, all identical, 25 meters in diameter, that are distributed in the north of America, and one is in Hawaii and the other is in the Virgin Islands. And of course, this gives you the resolution of a very huge telescope and allows you to do things with very high angular resolutions. You can get precisions of order 0.1 milliarcsecond. You can get resolutions of order 1 milliarcsecond, although an instrument like the Event Horizon Telescope, which works at 1 millimeter, gives you an angular resolution of 50 milliarcseconds, a tremendous resolution. But going back to the very long baseline array, more traditional, you get resolutions of 1 milliarsecond and precisions of order 1/10 of a milliarsecond, but the catch is that you cannot always use a very long baseline. The source has to be very compact and has to be very bright. So if you take a normal star, you will not see it. You need to go for objects that have processes such as synchrotron or as masers, and that are also very compact, and then you can do things. And with this technique, you can measure the subtle effect of parallax in relatively remote stars. Here's another plot, another graph of the very long baseline array, how it is distributed. Of course, they say that using the very long baseline array, you can measure a snail crawling on the moon. It gives you enormous resolution and enormous precision. Now, what do you measure in these stars? Well, in the stars, apparently the key mechanism is something that is called gyrosynchrotron emission, and it arises from the interaction of kilogauss magnetic fields with electrons that are mildly relativistic, let's say gammas of 2 or 3. And that produces an emission that is similar to synchrotron, but not quite. It's different. It's called gyrosynchrotron. For example, it is circularly polarized, while synchrotron it is not. And most of the emission comes from very close to the star, let's say a few stellar radii. And these are great tracers, point-like sources that we can really measure very well. And then we can measure them across a year and see how the source describes this apparent ellipse in the sky due to the motion of the Earth. Of course, parallax comes from, we all know, comes from engineering. If we know the separation between these two guys and the angle that the tip of the pine tree gives you along the two lines of sight, you can determine the distance, and that's the idea. Now, parallax, of course, the closer the star, the bigger the parallax. The more remote the star, the smaller the parallax. And somebody did this really fun simulation where they show a chunk of the sky. Here is Orion, right? We're going to be talking of the Orion Nebula, which is here in the sword of Orion. And basically what they did is that they did this thing, and then they put the parallaxes multiplied, I think, by 10 to the 5 or something, because otherwise you will never see them. And this is what you will see, right? In a year, one of these cycles will be completed. And of course, what is the closest star? Well, it's probably this one in here. And with that, you can get the distance. Now, what you actually measure is that besides the elliptical motion, you also have proper motions, secular proper motions, or linear proper motions between the two objects. So you have a line due to this difference of velocities between the two objects superposed on the ellipse. So what you get is like a helix. You get a helical motion, and from this you remove the linear component and you measure the size of the ellipse, and from that you can get the distance. Well, finally we get to Orion. This is the Orion Nebula cluster. Here is the famous trapezium. This is an image made with one of the infrared cameras in one of the BLT telescopes, and it's really an impressive picture. Actually, there are, in a region of about 1 parsec around the trapezium, there are several thousand stars. And of these stars, a handful show non-thermal radio emission that allows you to measure the parallax and measure the distance. And this is something that a young lady called Marina Kunkel did. And you cannot see this, but basically she did, I think it's actually 15 stars. These plots, which I now realize you cannot see, is just right ascension, position, and measurements made with time. And you can see that you see these helical motions, right? And then you have to fit them and determine the semi-major axis, and that will give you the distance. So what do you get? Okay, now, in here, in this axis, you have the distance to the source, and in here there is a numbering for the objects, and actually in here these different colors trace different regions in the sky. The one that we're interested with is the Orion Nebula cluster, which is this thing in red here, or in orange, okay? So every one of these points is a parallax determination, and all seem to crowd around 390 parsecs. Some have big error bars, and of course, statistically, you don't take them that much into account. But you can get a value from these 15 stars that is, gives you this 388 plus or minus 5 parsecs. This was part of the thesis of Marina Conkel, a student of Lee Harman. And the previous measurement, which was also done with a few of these stars, using 4 of these stars, gave 414 plus or minus 7 parsecs. And it was headed in a group headed by Carl Menten. And of course, one worries a little that these two measurements don't overlap at the 1 sigma level. Now, I think that it's just that we're probably both underestimating a little the error, and that the distance is probably 400 plus or minus 10 or something like that parsecs. And, but it's quite amazing that we're talking of distances that are of the order of 1% for Orion. When, I remember when I started in astronomy, the error was 20%. You would say 500 plus or minus 100 parsecs. But, so now, I think that you can use this measurement or an average of these two, and that gives you a fairly accurate distance to Orion. So if you have any questions, please stop me. This was made with VLBI, with very long baseline interferometry. And as I said, there are just a handful of the stars that you can detect with this technique. So if you want to detect more stars, then you have to go and accept stars that have emissions that are diffuse. For example, emissions coming from stellar winds or coming from a small H2 region. And then, of course, the restriction of the small size and the extreme brightness disappear, but you have to use the very large array, and you get a resolution of this order at 2 centimeters, and you can get positions typically a tenth of the angular resolution. And Sergio Zib, who is a student also of IRyA, now he's doing a postdoc in Germany, did all the stars he could see in a region of a few arc minutes around the trapezium. And here is the result. Here are the stars, and these arrows are, this scale is 5 milliards seconds per year, and this is a blow up of the central region. And he was able to do 88 stars, which is nice. In reality, if you go very deep, you get to see like 500 stars in the radio. In the optical, you see 2,000, and in X-rays, you see 2,000. But in radio, if you go very deep, you can see like 500. A recent study by Forbridge shows some 500 stars. But in here, this requires stars that are fairly bright, so you have to work with only 88. So from this, what do we get? We get in the plane of the sky the proper motion and its error in a right ascension and in declination. And you get like 1.2, which translates 2 kilometers per second to a couple of kilometers per second in each axis, and also in the radial velocity. Actually, I have it in here, but it doesn't appear. In the radial velocity, the sigma is also 2.5 kilometers per second. So this is all quite nice. The 3 axes give you the same velocity, which is what you expect if you have a more or less isotropic velocity distribution. You can also use this data to search for rotation in the stars, or to search for expansion or contraction, and we don't find evidence of known of those things. So it just seems to be a group of stars sitting in there with a dispersion of a few kilometers per second.
How do these proper motions compare with other star formation regions? Do you know information?
Well, one thing that was interesting is that these measurements for Orion coincide very nicely with those made by Herbig 30 years ago, which doesn't sound like much, but it's always nice to check. And in the other cases that this has been done, you get similar values, 1 or 2 kilometers. It's just very hard to see much higher. So this is a typical scatter dispersion in velocity that you see. And I don't think has been much effort to do many regions properly. But so taking in mind that the typical velocity is a few kilometers, you would be surprised to see objects moving at 20 or 30 kilometers per second. But these objects exist, and this is the last part of the talk. How do these objects form? So this is another way of looking at the SIB data, and this is right ascension. This is proper motion in right ascent, proper motion in declination, and you see most objects really cluster around 5 milliseconds per year, and you can feed them with a Gaussian that tells you that on the average the velocities are a few kilometers. But there are objects that seem to be moving quite fast, much faster than the typical velocity. And these sources are associated with something fairly amazing. Back in the 1980s, people working with the H2 molecule, observing the H2 molecule transition at 2 microns, detected an outflow, a very high velocity outflow of hundreds of kilometers per second in this region that is called the Orion BNKL. Why BNKL? Because there are 2 objects in there. One is the BN object, the Beckling-Neugebauer object, an infrared source, and the Kleinman-Low source, which is another region that emits in the infrared. And the trapezium is like in here to the southeast. So what you find in there is pretty amazing. In the H2 emission, you see these long fingers, they are called, that go in all directions. They are not totally isotropic, but they are not collimated either. When you do a molecule like CO, the 2-to-1 rotational transition, you see that there are fingers also, but they are shorter. They extend, let's say, a third or something like that of the longer H2 fingers. And these ones are shifted to the blue, and the red ones are, of course, to the red, which means that they are receding. Now, in the center of everything, there are a number of compact radio objects that everybody believes are tracing stars that are moving very fast at tens of kilometers per second and receding from a point in common from all the phenomenon. And that's what I will end talking about. Now, the mass in here, in the gas, is estimated to be at least 8 solar masses, and the velocities are quite high, hundreds of kilometers per second for the gas. So there is a lot of energy there, some 10 to the 47, 10 to the 48 ergs associated with this expansion. What Zapata did was to measure the radial velocity along the filaments, and what he finds is that they follow a so-called Hubble law. So this is the projected distance from the origin, and this is the radial velocity. These are the red fingers, the blue fingers. And you can see that they follow a linear relation, and these linear relations all point to a point at the center. And this type of behavior, with the more distant part moving faster than the nearby part, is the result of an explosion. If something explodes, of course, things are going to be thrown away at different velocities. The things that are moving faster, after some time, will be more distant, and the things that are moving slower will be closer to to the source. So this is let's say the trademark of an explosion. Recently, Bali using ALMA got this pretty impressive image. Again, here you see the fingers in blue and red, and he finds about 100 of these fingers going in sort of all directions. And again, in here are indicated the three stars that are moving away from the center of all this action. Now, the stars are moving at tens of kilometers per second. The gas is moving at hundreds of kilometers per second. So you get, of course, the gas is more distant in general than the stars. Now, fortunately, with the BLA, this region has been studied for a long time. And here are the three most bright and most interesting sources. One is associated with the BN object, the Beckett-Neugebauer object. Another is called the source I, which is quite interesting. And then there is a source called source N in here, which seems to be double. And, you know, the first measurements we did indicated over let's say, the last 10 or 20 years that this object is moving in this direction, this is moving in this direction. So if you make time go back like 500 years, everything was like in here some 500 years ago. And in here you can see the proper motions, which are in the order of 10 milli-arcseconds per year, I think. Well, anyway, they translate into, this is like 30 kilometers, this is like 15, and this is like 20 kilometers per second. So what happened here? And, well, what are these objects? That's a good question. The one we understand best is the BN object. The BN object seems to be simply an ultra-compact H2 region. There seems to be a B star there, ionizing a little region, and as the star moves, the H2 region follows with it. Now, source I is quite a mystery. It has associated a disk that can be seen better in masers, and that shows a very nice Keplerian signature. This is observations of the 232 gigahertz H2O maser made with ALMA by Ginsburg. And here you see, you make the cut along the major axis of the disk, and you see the velocities rise as you go to the central position. And from this, they get that it has about 15 solar masses. So that has a very nice disk of emission. Now, source N, we don't really understand what it is. So anyway, one thing that you can do very nicely is that both BN and source I, which are the sources, let's say, in the extremes of the image, you can do the relative astrometry between them. And this is very accurate because any systematic error will disappear. So you just measure the position of one source with respect to the other. And then you do the numbers, and you can calculate when they were closest and how close were they at that time. And you get that they were, in the epoch of least separation was the year 1475, plus or minus 6 years. This can be done with tremendous accuracy. And they were less than 100 AU of separation. They were very close. And this is a clue to what is happening there. And of course, here you see this is the year, and this is the separation in right ascension and in declination. And you see how it grows, right? It gets more and more separated. Well, here is another image, another very nice image from Gemini South, and you see the fingers in H2, and again the stars at the center. And you may ask, more of these explosions being seen in regions of star formation. Luis Zapata, who is a young researcher at the Institute, has really been trying to find them using ALMA data or submillimeter array data and looking for these filaments that show Hubble laws. And he has found a couple of sources, not as impressive as Orion, but that they have, there's an indication. Here is DR21, another famous massive star formation. And I don't think you can see the blue filament in here, a little filament in here, some red filaments. So there is not comparable to Orion, where you have 100 of these filaments. But still, if you look at those filaments and do the kinematics, you do see that they follow a Hubble law. Not as nice as Orion, but well, they do have a Hubble law. So maybe this phenomenon has repeated in other regions of a star formation. So let me just, to show you the motion of these objects, let me show you a comparison between 1991, where you start having good data, and 2016. And this is the source BN in 1991. This source is expected to move in that direction. So when you go to 2016, you clearly see that it has moved, right? Now, actually, we do this with many measurements in between to get better statistics. This is source I in 1991. It's supposed to be moving in this direction. So when we look at the 2016 data, we see that that's the case. And finally, source N is a problem because it's like double. And this is the 1991 image. All this is VLA data taken at 3 centimeters, 3.6 centimeters. And this is the more recent image where the source has become fainter, but it seems to be moving downwards. So we are very convinced that these three objects are moving. Some researchers come with papers saying that there may be something wrong, but in general, we believe we're right. Now, there is an interesting paper just published a couple of years ago, and this is done comparing near-infrared images of Orion. And let me, this is a paper by Lugman et al. So let me, here is BN, right? Here is I. Well, they don't see I, actually. And this is N. And the center of everything is supposed to be here again. So what they know two things, that between 93 and 2015, source N, which is in here and in here, doesn't move. Now, they don't give you the astrometry, but they tell you that it's not moving. But on the other hand, they found this source X, which is moving in this direction. So, they complain that source N is not moving, and the radio observations may be wrong. But they say, well, but we found another source that is going away from, it's actually going in this direction. It's going away from this position also. So we have new data, and we confirm the motions of source N. So what is happening, I think that most likely what is happening is that the infrared source N and the radio, the double radio source, are not the same object. The infrared source N is something that is stationary, while the double radio source is moving to the south. That's the explanation we have. And we have measurements. For example, this is the proper motions of source N. This is the year from 1986 or to 2017, I believe. And this is right ascension and declination. In right ascension, you don't measure motions because it's coming almost due south. But in the declination, you see that it's moving south. And but of course, the problem is that this is a little small. The source is kind of extended. So this is the position in 1985. And let me show you the position, how the source looks very recently in 2018, 30 something. So this is very, very recent data. And you can see that the source moves to the south, right? But it is elongated, and that's a problem, because to really be sure, we have to maybe wait another 10 years or 20 years, which I'm not willing to do. So you may see that the source is double, but it's not resolving this data. This data has a little less angular resolution, but you see that the major axis seems to have shifted between these two epochs. And indeed, that's the case. You can measure the convolved position angle of the major axis across the years, and you see a trend. Something weird happened at the beginning, but then over the years it has been moving. And if you assume it is a binary in the plane of the sky, you find that this binary system has a total mass of 6.5 solar masses. Now, Zib checked his observations, and he is proposing that there are two more sources receding from the position in common, but these sources are noisy. The proper motions are noisy. So let me again tell you, this is Bn, this is I, this is the source N. Source X will be like in here, also going away. And these cones indicate the uncertainties of the position of two objects, IRC 23 and Zapata 15, I think. 15. So if this is right, you see that we have 1, 2, 3, 4, 5, 6 stars going away from the same region. And this poses a serious problem for the models. And the reason is the following. At the beginning, when you had only like Bn and I that were clearly receding from the position, people said, well, what is happening here is the classic three-body problem. You have two bodies interact and they just separate, nothing happens. But if you have three bodies and these three bodies have a very close approach, then energy can be transferred in such a way that you form a binary, and one of the stars remains single, and there is energy to break the system. Okay, so I have talked with the people that does dynamics, and I tell them, can you produce this, but with many objects, with 5 or 6 objects? And they say, no, because even if the cluster was very dense, you have a very dense cluster, well, the most likely thing is that if you have a 2-star encounter, nothing happens, again, because 2 stars come by and just go away. But the most likely thing is that you will have a 3-body encounter, and these 3 bodies will form a binary and a single star, and then they will break from the system, they will run away from the system, but we have a hard time explaining so many stars, right? So people is trying to understand this and explain this, and it is not clear. The simple 3-body model is not enough. And even if you say, well, I take out these stars, right, and then the system is not bound anymore and it will expand at low velocities. And in here, these things are moving at tens of kilometers per second. So if you have any ideas, that they are welcome, but indeed this is something strange is going on in Orion. So Thank you very much.
Thank you very much for this very nice talk. And the talk is open for questions. John?
Thanks a lot, Luis. In the three sources you have been studying, the source Kn, the source I, and the double source N, is there any hint of variability in the structure also while they are moving away? For the double one, it looks like.
Well, the changes in I is more like due to the beams. But in source N, and that's another problem, source N, one of the sources had an ejection in around 2010, and that changed the morphology a lot. So this is the point. Bn is fairly steady, but certainly N has shown changes in morphology, and that also complicates the interpretation. And source I think is actually doesn't change that much, and probably just the big difference that you saw was that the new data has more angular resolution. But I think that there is no clear evidence. But in source N, yes, not only the two things seem to be rotating, but the southern source ejected like a jet. So all these things complicate matters.
Survive to the explosion. I understand the explosion in this place, and I am wondering how can this structure survive?
That's a good question, because if there was a close interaction, it was an interaction to get velocities of 10 or 20 kilometers, you have to get things a few AU close, and the disk is like 100 AU, so the disk was probably dissipated. Now people has looked into this, and they argue that in 500 years you have time to rebuild the disk. I haven't really done the calculation myself, but the argument is that you can rebuild the disk. But what you say is interesting, because also another thing you can say is how it is that this binary N source, which is a binary, didn't break if there was this close encounter. You know, because it separated 100 AU or something. So these bigger structures, how did these bigger structures survive the explosion? Now, in the case of the disk, people supposedly has done the numbers, and they argue that you can rebuild the disk in 500 years. But then, this binary is a fairly weak binary. How did it get into the multiple body interaction, and it got ejected without breaking? So all this points to me that there wasn't an explosion properly, but more something that just smoothly, sent things away. But I don't know what it was, because you have things that don't adjust well.
I just wanted to make a comment to what you were saying now, because so I've been studying other star-forming regions in which, from the comparison of rotational periods of very low mass stars, there is an argument saying that, so how can I summarize it? If the region is very dense with a lot of gas and stars, then the probability of, due to interactions, not to lose the inner parts of the disk for the stars is higher, and then the stars can speed up when they contract more than in other regions in which the stars keep the whole disk for longer times. So this goes a little bit against the comment of the disk of the star being able to reconstruct after an interaction. So I support your view, what you mentioned just at the very end, that maybe the expansion, it's not explosion with a lot of energy involved, but slower movement part.
Thank you.
results compared with the Gaia results? I imagine that for these particular objects, they are so deeply extinguished that they cannot be observed or detected with Gaia. Is this true? Is this the...
Well, exactly. For example, source I is very hard to detect. It's not seen by Gaia. But then in several of the objects, Sergio Sib also has made a comparison between the VLBI proper motions and the Gaia, and they coincide lovely, beautifully, yes. Yes, he was smart enough to do this quickly because otherwise other people would do it. And so there is a great agreement, yes, to a very small fraction. But then I guess that the VLBA has a niche in the sense that some types of stars will not be seen by Gaia. But when you have an optical star, Gaia just beats you totally.
Thank you very much for such a nice talk. I have a question. I'm not an expert on the field, so I'm completely ignorant about what could have made the origin of this thing, whatever, an explosion or whatever different thing. Is there any other tracer that you could use to have more hints on what happened? Maybe in, I don't know, in X-rays for the shocked gas or whatever?
That's a very good question. I don't remember the region being detected in X-rays, but I may be wrong. The stars are detected in X-rays, thousands of stars. I don't remember the shell being ejected because it is, I mean, the filaments being ejected, being seen in X-rays, but they should because they are moving quite fast. So I'll check on that. I really don't know the answer.
So no more questions. Thanks again to the speaker.